All right, so we're going to switch to the next session on today's agenda. And for all of you who are participating or who started looking at the CTF, like we said, you can reach us at on the Telegram channel that we shared, and hopefully you've already got the GitHub. But if you don't, then reach out to any of the volunteers who have these T-shirts on, like this, for the CTF or for any other questions. So thank you.
Thank you, Rajiv, for the fantastic, and the Secure Realm team for the fantastic introduction to the CTF, and also helping us, the volunteer team, for the whole DeFi Security Summit. Well, this, as some of you know, this event last year was started last year, and it's a recurring event. And last year we had an opportunity to have Natalie Chin from 12-bit doing the security track for us, and she agreed to do it again. Natalie is a leader in the security research. She is working on basically their security tools, and Kidna, Slither, and others, and she's gonna present, right?
Yep.
Thanks.
All right. So yeah, I'm Nat. I'm from Chairlabits. And today I'm going to be talking about how to write safe smart contracts and kind of the, I'm just going to close this, keys to writing safe code. A little bit about me. I'm Nat. If you want to find me on Twitter, my handle is here. At Chairlabits, I'm a security researcher. So that means I do security reviews. I work on tooling, and I get to attend conferences like these to show how we're using tooling, and kind of talk about the public resources that we have available, just to make sure that they're as accessible and as available as possible. Personally, I'd love to climb things. I like to fall off things, and generally that means I'm falling off rocks just around the world. On the Chairlabits side, we like to try to essentially help people build safe software. What that means is we do a lot of research and engineering and R&D based on how to make sure that code is as safe as possible. But that means that everything that we learn from our research feeds into the creation and the development of our tools, which are all open source. You'll probably be familiar with a few of our tools and like our kind of skill set. Slither, Echidna, Medusa, and a few other tools that help essentially make that developer experience a little better. So I did say I was a bit of a climbing nerd. In climbing, generally rock climbing without protection is kind of a life and death situation. If you're climbing without bouldering mats or you're climbing without clips and carabiners, it's something that's considered fairly risky. The safety considerations that we consider in rock climbing are very similar to that of how to think about like smart contract security. We work really hard essentially to try to solve either man-made problems or natural problems, but a little bit of beta, which is essentially tips and tricks on how to get up a route, goes a very long way to actually understanding and solving a problem. So in this particular comic, the bottom beta in the bottom, it basically tells you in order to climb a route to either grow taller or just be better at climbing, which obviously is probably not the best advice. If we tie the concept of beta back into kind of smart contract security and security in general, there is a parallel around, like, for example, a Stack Overflow question and like the solution. If you consider asking a question on Stack Overflow, the beta is basically the answer. It doesn't necessarily matter what this question is even asking. But we're going to be talking about, I think I skipped. We're going to be talking about how to write safe code and how to write safe contracts. The beta here is probably going to be fairly self-explanatory and kind of something that should be easy to follow along with. And the whole goal of this is to create kind of somewhat of a framework and some more understanding around what would help security researchers in understanding your code base and what would help with making sure your code base doesn't have bugs while you're developing. So essentially allow you to catch your bugs as early as possible. So in climbing, we also have this concept of a start hold. This is where you start with your problem. This is where you start with your climb. Generally, this is marked with a start marker like this. So in this particular problem, you have to start with four limbs on that big square volume, and you have to essentially jump over to the others. This defines essentially what is the end and what is the beginning of your route. So in order to start, let's figure out where exactly we should start. This is an interesting concept because specifications, even though they're probably the dullest to write, are the most important to have for your code. By figuring out where you're going, there's a much better chance that you're able to determine how your code is not working properly. When you create specifications, this should include information like what are you actually trying to build, who your users are, and how your users are going to end up using your code, and especially how your code is intended to be used. Outlining these mean that you have a target to reach. Having these means you have a target to reach, and it also means that you have the ability to know what future features you might want in your code and what future areas you want to extend your code in. So in terms of what a good specification should include, there's a whole lot of information that could go in these specs. And so this is kind of a highlight of what would be the most important. Generally, when we're writing code, we make a lot of assumptions around your code is only supposed to work under certain conditions, or a user calls your function with a certain input range, or the endpoint or the caller of your contracts is supposed to be a certain address. If you are writing down all of the assumptions that you're making and including that in your specifications, it means it's much easier in the future for someone to be able to read all those assumptions and understand when this code is supposed to work and what is supposed to happen if those assumptions don't actually hold. We'll be coming back to ways that we can verify that the assumptions actually hold. And there's a multitude of ways that can be done. But having those assumptions and having that in your specification is going to go a long way to actually understanding what code you actually want to check and what you want your code to do more specifically. The other benefit of writing down all of your assumptions is that you're then also able to identify all of your edge cases and cases in which your functions are supposed to work. So if you have an idea of how your function or how your code is supposed to work under the proper inputs, then you should be more able to actually analyze the edge cases and cases that fall outside of that. If in the case that you do have any mathematical computation and kind of assumptions, proving any kind of formula is going to be very useful to actually check that your math works as you intend. One common thing that we see generally is just that there's an assumption that like a math function is supposed to work under certain inputs, but that doesn't actually hold for the entire subset. Another thing that should be included in these specifications is how a user is supposed to interact with your system. So having a list of features and functionality that a user can perform is one thing, but also having the full call stack between what function a user calls and what functions and different checks get invoked after that is going to be very useful to actually check that you're doing A, all of the data validation that you need to do, and B, checking that you're actually making all the state changes that you need to make. So that ties into data validation assumptions as well. By that we mean if your function is callable by an only owner modifier, then what other checks do you need to make based on the other inputs that are coming in? For all of the functions where you have even publicly callable functions with like arguments, are you actually doing the proper data validation that needs to be done? Another aspect that's important to outline is when your code is actually supposed to work. So when is your code reverting and when it should be successful. By writing down all of the cases in which your code is actually expected to revert, that allows you to have a better mental model of your architecture and allows you to see essentially end to end if your system is if you're interacting with your system in one way, what impact does that have on your code base? And on the other side, specifying when your code base is, or when your function call or et cetera is expected to not revert. Outlining these is not just important for implementing automated testing, but is incredibly important for actually understanding how your code is expected to work. Going more into kind of the code side, having NatSpec on all of your publicly callable, or on all of your functions is useful just because you're able to specify essentially understand what the function does, what are the inputs that are expected to come in, and what are the expected return values. From that, you have a much better idea of, per function, what is expected to happen. This is one thing it sounds very easy, and especially if you have a small code base, it may be easier to do, but as your code base grows, having NatSpec is going to be even more important to actually identify how all of your functions work together and isolating logic in between those different functions. So similar to user flows, another thing that a good specification should have is creating user guides. Essentially, a user guide is outlining how a user is expected to interact with your system. If they're going to be specifying, for example, slippage values, how are they determining like what slippage values to choose, and kind of examples in terms of how to choose these inputs. The benefit of this is that once you have all of this whole list of what a good spec has, it means from a review perspective and from a developer perspective, you know what your code does, and that assumption is the most important. Once you have it all written down, it becomes a lot more concrete as to what the code is expected to do. So the benefits is basically you know what your code is supposed to do, and you know how it's supposed to work. So it's not just, my code implements a liquidity pool and it does swaps. That's a bit too vague to actually verify that it has or to check that it has no bugs. If you have these detailed specifications, it's much, much more easy to essentially determine what the impacts are. So that brings up an interesting question, because if we're writing down everything as we're creating these specs, it doesn't necessarily mean that our spec is with something that we create once and then leave it as is. The assumptions that we essentially are making for like writing this code is generally something that changes with time as we're adding new functionality, as we're making new changes to the code base, making sure that that spec is up to date and essentially updated every time you change code, in the same way that a unit test should be written for every function you add, is a way that you can make sure that that spec is always live and always reflects essentially your most recent changes as well as your most recent assumptions. There's generally a confusion with especially code bases where we have outdated documentation and new code. So then, is your code the single source of truth? And if it is, how it's very unclear how to verify how your new code is expected to work in comparison to previous versions that are documented. So that's quite a lot about specifications, and that's one tool that we can use to essentially be able to help us essentially identify what assumptions we've made on our code and make sure that those are explicit. But there's a lot more tooling that can be used to help us make sure that we're actually making sure that our code is safe. So also with climbing, we have this concept of tooling as well. Generally, on really big walls, we'll have like ropes, carabiners, anchor points, where essentially you can see on the picture on the right, there's just an insane amount of rope and gear. All of these tools are basically used in order to keep climbers safe. If they fall, they'll end up dangling in midair, but they're not going to the ground. Similarly, we have these kinds of tooling with blockchain security as well. One thing with tooling in specific is we should be making use of these tools whenever we're writing new code. You don't want your anchor points to look broken and in pieces like this. Unit testing is one of those anchor points that can essentially help you determine, in combination with your specs, how your code works and what is it supposed to do, and does it actually do what you intend it to. So it's an interesting conversation to have, because you need your specs first. You need to essentially identify what your expected behavior is. And then you need to identify essentially what is the happy path in terms of, if a user is going to interact with your system, what are how is your system expected to work under the proper inputs, under the assumption where everything works, and the user inputs like all the correct inputs. The unit test should essentially be testing that entire flow for all of your functions, but it should also be testing the unhappy path. So this would be if your function is either reverting or not working correctly. Is it reverting in the right places? Is it under inputs that are malformed or incorrect? Does that have any impact on the system? With your specs, once you've written down all of your assumptions, it then becomes very easy to identify what your edge cases are. Edge cases being cases where you may not have considered maybe the upper bound of like a UN 256 and like the lower bound. Generally, we recommend that everyone's testing the full range of inputs. So they're testing essentially the expected input range as well as the edge cases in the unexpected range. Another thing that is definitely beneficial in unit testing is having at least minimum 100% statement and branch coverage. The benefit of this is that you're able to essentially check your system under the inputs that you've provided. So this helps you, if like you can specify, certain inputs, certain checks that you want the code base to hold true. And under those cases, this 100% statement and branch should help with essentially checking against those specific input ranges. Then the benefit of unit testing becomes we should be able to use unit testing to find how the spec is different from the actual code. From the spec, we should essentially have those list of expected behavior and assumptions, and from the code, we should be able to check those. Another thing is it does force you to write testable code in that it forces you to separate logic into smaller unit tests, into smaller functions that you can easily pick up and test logic against. This is beneficial because you can then do unit tests against individual functions, and then you can pick up integration tests with different modules. As long as you're updating code, these unit tests should be written alongside this code. It means every time you're writing a new function, you should be checking the correct input ranges, the edge cases, and making sure you're hitting that expected coverage. The benefit of this also means that in the future, if you're changing your code, you're refactoring, it future-proofs you from reintroducing that bug in the future. If you do actually reintroduce that bug, your system will essentially tell you that there is a unit test failure. The whole goal of unit testing and these tools in general is basically to identify bugs as they're being introduced during the development process, as opposed to thinking about security at the very end. There are, however, limitations of unit testing, and this is generally in that the coverage of your tests are only as good as the inputs that you've actually tested against. So if you're, for example, your function works against UN 256, and you've tested maybe a smaller subset of that bound, if you're not testing the lower bound or the upper bound, those unit tests are not really conclusive. So even if you have 100% statement coverage on that kind of function, not testing those extra edge cases means that that unit testing isn't able to uncover bugs in those areas. The other thing, of course, is that it doesn't test integrations between components. So if you have a DeFi protocol set up, you're integrating with multiple other DeFi protocols, unit testing is not going to help you identify either how there are deviations in expected behavior with those external calls, but it's just going to tell you essentially per function. So going back a little bit to climbing, generally with climbing hold, we have a series of climbing holds, and a jug is essentially the best hold that you can get on a route. It's the one where if you're trying to jump in midair, jugs are the holds that you're aiming for. Obviously, as you get more and more challenging and challenging routes, then you essentially get into the bottom part, where it gets smaller and smaller and it gets harder to actually hold on to. So this is how a jug would be used, generally a jump. We love them just because they make our lives much easier. They make routes much easier to climb, and they're basically like monkey bars, but maybe a different shape. So in a similar way, static analysis is basically your jug. It's your automatic bug finder. If you were to imagine security researchers or auditors going through code and just maintaining a growing list of vulnerabilities, going through wrecked news and writing down pretty much all of the reasons for previous hacks and identifying smart contract best practices. The accumulation of these essentially determines would give you like for example, a list of like all the ways that protocols have been hacked or like functions have behaved incorrectly. If we consider Slither, Slither is basically taking that huge list and applying analysis on your code base all statically. So it's basically looking out for any kind of best practices within your code base, and especially any kind of violations. So we could go through that manually, and probably a lot of the time, sometimes people do. But one benefit of Slither is that if you're running on a code base, it can essentially tell you instances where reentrancy might be possible. It's not going to tell you this is 100% exploitable, because that's not something that static analysis can do. But what it can do, it tells you what might be a problem. And so the previous example here is output from Slither action. So this is integrated into the GitHub CI platform. And what this basically shows is a code snippet and it outlines a potential area where reentrancy might be possible. As security researchers and developers, this would be our chance to go in and actually check whether is it making an external call, is it handing off execution flow to someone else, that kind of thing. So again, Slither is going to analyze your code statically, which means it's just going to check against the best practices, but it's not necessarily going to tell you that something is 100% exploitable. Right now, it matches 87 best practices or detectors to essentially determine and find these vulnerabilities. So that brings up an interesting question, because once we have Slither findings, what do you actually do with it? If it's currently exploitable and it's currently a problem, that should be a sign that you should just fix your code. Essentially, if it's for reentrancy, add a non-reentrant guard or use checks effects interactions pattern. If the code can potentially be exploitable in the future due to like governance updates or some other code upgrade that might be possible, then that would be a case in which you would want to document and make sure that it's explicit that any kind of code update in the future will essentially will have these impacts on the system. So similar to unit testing, Slither also has its pros and cons. It runs quite quickly on code bases, which means that it gives us quite a quick view of what might go wrong, and it tells you what looks wrong, but it's not going to tell you what is exploitable. It's going to tell you there are violations of best practices, but it's not going to specifically say this is exploitable in this way. It requires human interaction to go in, triage, and determine what the impacts are. So in climbing, we also have this concept of a crux. This is the hardest part of a move or route. This is the part where you usually have to fight the most. This is essentially the most challenging part of climbing. And in the blockchain security world, this is basically fuzzing. Fuzzing will stress your code with random inputs. So kind of like a cat on a keyboard or a monkey on a keyboard. It's basically in, like, for example, that function that takes in a uint 256. Instead of being defined by the input range of a unit test, fuzzing is essentially going to generate pseudo-random values in order to test the breadth of how that function works. Fuzzing does also force you to identify how your system is expected to work through the creation of system invariants. In some ways, you can think of fuzzing as a robot unit testing, in that the fuzzer is going to determine what are the inputs to check, but as a developer or as a researcher, our goal is to essentially define in code what are those assumptions that we've made on how the code is expected to work. The other area of fuzzing is that it can be slightly more difficult to actually set up an end-to-end infrastructure, and especially as you get into more complicated bugs, can be difficult to get stood up. So in terms of tooling, we have Echidna, which is our open source smart contract fuzzer. And it will automatically generate inputs for your functions. So based on the properties that you define, or those assumptions that we were talking about in the documentation section, those are essentially converted into code, and then Echidna runs on a code base to determine, A, is it possible for those assumptions to be violated, but also, if violated, what inputs actually cause that violation. The benefit of fuzzing is that it provides more complex bugs and quite a large, quite an interesting subset of bugs that may not have been uncovered through unit testing. And it can help us better with determining those edge cases. Generally, it's considered more complete as unit testing, but the setup and the getting stood up with contracts can be a little bit more difficult. So going back a little bit to climbing, generally before we hop on a route, we're doing a bunch of rope checks, safety checks, belay checks, making sure that we're all tied in, making sure all our ropes are in. And basically after all of that, the comic ends with, I don't want to climb this route anymore. But we can still climb the route. Tying this back to the blockchain safety side, one thing to keep in mind is that blockchain, or security in general, is a continuous process. So it's not something that you should be doing all your development and then thinking about security. It should be something that you're essentially thinking about security as you're writing code. Generally, as a practice, write everything down, even assumptions that you think might not actually be relevant in the future. Having those written down in any form is going to be very useful. That means adding unit tests as you're adding functions, running Slither as you're adding new code, determining and identifying invariants as you're building out your code base, and then running fuzzing tests and making sure that those properties hold. So we're right at time. If you want to learn more, this QR code is basically a link to securecontracts.com. And this provides a lot more information around development guidelines, incident response plans, and how to create them, more guidance on how to get Echidna stood up and examples of what those code bases look like, and way more. So yeah, thank you.